Welcome to Lecture 2.2, the derivative as a function. In the last section, we mainly focused on finding the derivative of function at a specific number. And remember, whenever you see a in any formula, that's talking about a specific value of x, like x equals 2, x equals 1, etc. So in the last section, we were primarily focused on finding the derivative, f prime, at a specific value, again, like 1, 2, etc. And we had our derivative equation here, or the definition, okay? So some initial point, y, and then some point further along x, because the next value of x is a plus h, okay? Here, what we're going to do in 2.2, and we already saw a preview of this in 2.1, we're going to change our point of view and let the number a vary. And what that means is we're going to find the derivative over the entire function of f. And so instead of finding the derivative at one value of x, we're going to find the derivative at all values of x. Basically, we're going to find a formula or a function that will give us the derivative at any point along the function. And so notice here, the only thing we have different is instead of a, we have just the generic variable x. So it's the same formula, but it's f of x plus h minus f of x over h. Okay? So let's look at this and see what this means visually. Okay? So the graph of a function is given here in figure 1. Okay? So we can see that, remember, our derivative is the slope at any specific point. So what are some things we know about this slope? For example, where my arrow is pointing all the way down here to about 1/2, we know that the slope is negative because it's going down from left to right. As soon as we cross over 1/2, it's now increasing again, so we know the slope is positive. So the derivative is positive. And in order for it to go from negative to positive, somewhere here in the middle, it has to cross 0. And notice this happens when we have a maximum or a minimum. Because again, here we're going positive and then negative. So here we have a slope of 0. Okay, and then we go negative, negative, negative. We hit a 0 point down here again at this minimum, and then the rest of the slope is positive. So one of the things we can do, first of all, is identify the kind of those places where the slope is 0. And again, these are at the minimums and maximums. The minimums, so we have a minimum, a maximum, and another minimum. This actually calculated some slope here, so you could have a value there. And this is not given in the formula, so I think this is a little bit of a cheat. So I'm not worried about point P. Now notice that from the beginning of our function to point A, the slope is negative. So notice down here, our slope or our derivative is going to be negative until we hit point A, where the slope will be 0 again. And then it'll be positive until we hit point B. So notice what happens here is it's kind of increasing, and then it's decreasing again. So we have this little maximum here, this little parabola, because between A and B, it has to go from 0 to positive, but then it has to go back to 0 again. So we go 0, positive, and then negative back to 0 again. Okay, I'm sorry, it's not negative. This is where it gets a little confusing intuitively, because this is the slope of the derivative of the first derivative, which would be the second derivative. Okay, but notice here, the slope of the derivative, the slope of the function between a and b is positive, so the derivative stays positive the entire time. Notice this is the graph of the derivative, and it's always above the x-axis, so it's positive the entire time, although its slope does change to 0, but this would be the second derivative, which we haven't talked about yet. And then it goes back to 0 at b. It's going to be negative between b and c because it's going down. So again, we're going to go down and then come back up to 0 at c, and then it's going to be increasing from there on. And we're not going to talk about this point. So this is a really important slide for you to understand about how to conceptualize the derivative, remembering that the derivative is the slope at any single point. And so we know some things from algebra about slopes going down or negative, slopes going up are positive, and then in between the two, the slope is 0. And think about that, because what's happening is the tangent line, as you can see it here better, is a horizontal line. And remember that horizontal lines have a zero slope. Horizontal lines have a zero slope. So this is something we're going to be using in calculus, and this is one of the more powerful tools of calculus to know when the derivative is zero, because it represents a max or a minimum of some kind of function, which we often want to know about. For example, if you're a business, you might want to maximize your profits or minimize your costs, etc. All right, so now let's look at a problem. If f of x equals x cubed minus x, find the formula for f prime x, or the derivative f of x, okay? So we're going to use this, it's really the same, similar setup, except we just don't have a value, a point value in this like we had before a. So we're going to use the formula, and remember when we use this formula, all we do, everything is given to us. For example, h is a given, it stays there. F of x is usually given in the problem, and it stays there. So in order to calculate the derivative, the only piece I really need to figure out for this formula is what is f of x plus h. I find f of x plus h, remember, by substituting in x plus h wherever there's an x. So I have x plus h cubed minus x plus h. And again, whenever I have minus, it's very important that I put what's after it in parentheses, so then I then do the distribution. Now here I have a little bit of a more challenge here, because I have to actually FOIL this out or multiply this out so that I can simplify. Okay, you should be able to do this, and I'm not going to go through the steps of foiling that. X plus h, it is not x cubed plus h cubed. And if you're still doing that, you've got some algebra review that you need to do. This is a FOIL problem, and you'd have to FOIL it twice. So when I multiply x plus h times itself 3 times, or cube it, I get this, minus x minus h. Again, distributing the negative. Slow down with these. This is where I see a lot of mistakes. Minus x cubed, and again, minus a negative x is plus x. So make sure all of your f of x is in parentheses too. Now I kind of play that go fish game and cross things out that are common, x cubed, minus x cubed, minus x plus x, etc. And so I'm left with this formula here once I cancel out the opposite terms. Notice once again, I have an h common across the numerator. So if I factor that h out and then cancel it out with the h in the denominator, I get simply that we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1, which again, remember, since h is going to 0, this term goes away. 3x times 0 is 0, plus 0 squared is 0, and I'm just left with 3x squared minus 1. So this is the derivative at any point along this graph. All right. So here's another example. Why don't you try this example? And I put this little pause here so to suggest that you pause the video, try to do this one on your own, and then hit play again and see how you did. Okay, so now's a good time to pause. I guess I should have put 2 pauses there. Anyway, let's move on. So the first thing I'm going to do is, again, apply the formula. I have f of x right there. I have h right there. The only thing I need is x plus h. This is relatively simple. And so I have the square root of x plus h minus the square root of x all over h. Now remember, in chapter 1, when we were solving limits like this, we had to do some creative things. And when we had radicals, we tended to multiply the numerator and denominator by the conjugate. And so that's what we're going to do again here. We're going to multiply the numerator and denominator by the conjugate here of the radical. And notice we can do that because what we're multiplying by is actually a factor of 1. Because anything divided by itself is 1. And 1 times anything doesn't change the value of that thing. So when I do that, the numerator becomes the square of the first term, which is x plus h, minus the square of the second term, the square root of x squared is x, all over h times the square root of x plus h plus square root of x. And here, notice that what happens is I get x plus h minus x, so the x's cancel out, and I get h over all of this term. And so the h's cancel out, and I'm left with this following limit here, which again, remember the h goes to 0 now. Now I can apply the limit I couldn't apply it up here, remember, because we'd have 0 in the denominator, so we had to do some algebra. And x plus 0 is just x, so I get 1 over this 2 times the square root of x. And this is my formula for the derivative at any value of x along this function where it's defined. All right, let's try another example 4 here. Now this one is a bear, okay? Because it's a rational expression or a fraction that we're going to put into a fraction. So this one's going to be a little bit more complicated. Again, you might try it or go along for the ride, okay? So now remember we have f of x, which is just there. We have h, which is just there. So these two parts are certainly fine the way they are. And then we have to find f of x plus h. So we get 1 minus x plus h. Make sure it's in parentheses because it's subtraction. 2 plus x plus h. Wherever we had an x in our original function, we now put x plus h, as you can see here. Now, in order to simplify this, since we're subtracting fractions in the numerator, we have to have a common denominator. So the easiest way to do this is to use the product of both of these as the denominator. Remember, common denominators have all factors. So our common denominator is 2 plus x times the quantity of 2 plus x plus h. All right? So that means we have to multiply this numerator by the missing piece, 2 plus x, and this numerator by the missing piece over here, 2 plus x plus h. And you can see that's happening here. So this numerator times 2 plus x minus this numerator times 2 plus x plus h. Again, we have two longer FOILs here. They're not really FOILs, but I use a box technique to multiply these out. I'm not going to do that. That's algebra, but you should try to make sure you can do it instead of just watching as we go along. These are probably the more complicated problems. They're not extremely difficult, but they are easy to make mistakes in them. So when I multiply these two polynomials out, I get 2 minus x minus 2h minus x squared minus xh. When I multiply these two polynomials out, I get 2 minus x plus h minus x squared minus xh. And I have to remember that I'm subtracting all of this, so every term is going to change signs. And so when I do that and simplify the 2 minus the 2, the negative x plus x, etc., I get left with just negative 3h. Everything else cancels out up top. I get negative 3h over that long involved product in the denominator. And so I can see the h's cancel out, and I just get negative 3 over this. Now I can apply my limit as h goes to 0 into the denominator because, again, at this point now, the denominator is not going to go to 0 if I make h 0. And so I get this formula, negative 3 over 2 plus x squared, okay? Because you can see here I get, when h goes to 0, I get 2 plus x times 2 plus x. I know I went through that fast, but again, you can rewind it, you can watch it, you can try to do the steps in here to make sure you can solve it as well. Thought I had a graph there, but I guess I don't. So I want to give you some more notation pieces. We've been using f prime or f apostrophe x as the derivative. Remember, f of x is y. Another form of notation says y prime. We can also do dy dx. This is later notation by Leibniz. Df dx, d dx of f of x, capital D of f of x, and also d sub x of f of x. Now, these last three are actually called differentiation operators because they're telling us to take the derivative of f of x, take the derivative of f of x, take the derivative with respect to x of f of x. Okay, so they're differentiation operators because they indicate that we should be doing differentiation, which is the word that we have for finding a derivative, just like sum is the word for addition. Okay. So again, that differentiable replies to the act of finding a derivative, and we say a function is differentiable at a if the derivative f prime a exists. Okay. So if we can find a derivative at a, then it's differentiable at a. We say it's differentiable on an entire interval, and it's an open interval. We're not including the endpoints because we don't really know what happens at endpoints after potentially. And notice the endpoints could be infinity, so it could be the rest of the function, or it could be all values, if it is differentiable at every number in the interval, okay? So we're saying that a function is differentiable on an open interval or for all numbers if you can find a derivative for all values of x or for all values of x in an interval. Now notice this a and b does not represent an x and y. These are two x values. Remember, an interval tells you where to begin in x and where to end in x. And so this is saying go from x equals a to x equals b. And it doesn't include those values. Those are open-ended points. That's why it's called an open interval. And then we have theorem 4, which says that if a function is differentiable at a, then the function is continuous at a. And remember, that's when you can keep your pencil on the graph paper. There are some places where a function is not differentiable, and these are the three main places. Notice if we have a corner, a point in a graph, a sharp turn, because notice what's happening here, the slope is positive, and if it's got a point there, then it's immediately going to negative. It's not going like here where we go from positive to negative in a smooth curve. We find a space where the derivative is 0, but when you have a point, there is no place where the derivative is 0, so it kind of misses that value in the very middle, okay? Notice also if we have a discontinuity, if the function is not continuous, then we can't find a derivative here, because notice as we're going along this graph, we kind of stop here, and again, it may be 0 there, but we're not sure, and it may be 0 there, but we still have a jump here or discontinuity, so the derivative at this point is not going to be the same at the derivative at this point, and so we have a problem here, okay? There's also one other case, if we have a really sharp curve down, that we could actually have something that the tangent line could actually be a vertical tangent. And remember that when you have vertical lines from algebra again, the slope was undefined. And if it's undefined, remember the slope is the derivative, so we have no derivative here. It's not differentiable when we have a vertical tangent. So the three places that a function is not differentiable is if we have a corner or a point, if we have a discontinuity, a jump, or if the curve goes so steep that it creates a vertical tangent. So those are the three places where a function is not differentiable. One of the last things we're going to look at in this section is something called higher order derivatives. And so remember, if f is a differentiable function, then its derivative, which we annotate by f prime, is also a function. So the derivative of f is also a function. And since it is a function, it can have a derivative of its own. So since f prime is a function, it can have a derivative itself, and this is denoted by f prime prime. And this is called the second order derivative of the function f. So let's look at an example here. If f of x equals x cubed minus x, find and interpret f double prime x. Well, remember we just found a few moments ago that the derivative, the first derivative of f of x equals 3x squared minus 1. This is about 3 or 4 slides ago. So in order to find the second derivative, we first have to find the first derivative, which we did, and take the derivative of this. So we just put it back into that same equation. But notice now the second derivative equals f prime x plus h minus f prime x, etc. So it's doing to this function what we did to the original function to find the first one. And we could continue to do this for the third order derivative, fourth order, etc. Okay? So again, remember that f prime x is given to us, h is given to us. The only piece we have to find in this formula is f of x plus h, in this case f prime of x plus h. Here's f prime, and so wherever there's an x, we substitute in x plus h. So notice we get 3 parenthesis x plus h squared minus 1 minus f prime x, which is 3x squared minus 1, again in parentheses all over h, We're going to FOIL this guy out, square him out, which you see there. I'm going to go through this wicked quick because this is the third or fourth one we've done. And we're going to reduce this. We're going to factor out the h, and we get left with 6x plus 3h. Again, if h goes to 0, this term goes away, and we get simply 6x. Now here's an interesting graph of the function, which is the lightest curve here, the first order derivative, and the second order derivative. These, I'm pretty good at intuiting math, but these are not very intuitive for me. So I really have to take my time, and part of that's because I get confused with the slope of the derivative versus where the value is. So notice here, we go from, on this first function, the lightest one, we start with a positive slope, and we get to a max somewhere around here, okay, where you can see my arrow there, somewhere around -1. So remember that the derivative, the first order derivative, has to be above the line because the slope of the function is positive. And even though it's coming down, which its slope is negative, all the values of the derivative before we hit this maximum are positive because they're all above the x-axis. And that's the confusing part, because I go, wait, this slope is positive, why is that one negative? Because the values of the function are positive, which relate to the slope. Now its slope is negative, and we'll see how that relates to the next derivative. So it becomes 0 at this maximum. It's going to become 0 at this minimum here. And we know that between this maximum and this minimum, it's all negative slope of the original function. So our first order derivative is going to be in negative values or below the x-axis, and then it's going to be positive the rest of the way through. So now to look at the second derivative, remember this is just the slope of the first derivative. And so we can see that we have a minimum right here, it looks like right at x equals 0. So our second derivative has to cross through 0 where we have this minimum value. Before it, the slope of our first derivative is all negative, so all the values of the second derivative are below the x line. Then where we have the minimum, it crosses 0. And then after that, the slope of the first derivative is all positive, so all the values of the second derivative are positive. Now, I know that was a mouthful. You may want to listen to that again. I tried not to go too fast. I know I can sometimes when I'm looking at graphs like this. But take your time and make sure you understand it. This is a really important concept again, and also to be able to see it visually like we did before. Okay. So let's talk a little bit more about these higher order derivatives and try to get to some understanding with them as well. So f prime, or the first order derivative, is the instant rate of change of function f. So f double prime, which is the second derivative, is the instant rate of change of the first derivative. F double prime, instant rate of change of f prime. Second derivative is the instant rate of change of the first derivative. Third derivative is the instant rate of change of the second derivative, and so on. Actually, and once we get beyond 3, we actually write small numbers up here like exponents. So the fourth order derivative is f. It looks like it's raised to a power of 4, but it's just the fourth order derivative, and 5 and 6 and so on. Now, there's a good example to understand how this relates, because when you get to remember the first derivative is the rate of change. So what we're saying here is the second derivative is the rate of change of the rate of change. And that can be a little bit difficult, intuitive as well. So the best thing to do is to slow down and think about what each of these is. And here's a good example. So let's take the position function s. Remember, this is the function we drop the ball off a roof, or we're driving our car. S is the position we're in. So we start at position 0, our home, and over 10 minutes we drive 10 miles, and so the next position is 10 miles away, or the distance is 10 miles. Remember, if we take the derivative of the position function, how our position is changing with respect to time, in the example I just gave with driving to work, then the first derivative is the change in position over time, or miles per hour. It's how fast that is changing, right? Or the speed. We already looked at that. Well, so the second derivative of position is how our speed is changing. Now, what does that mean? Think about it. You're driving along to work. Let's say you're driving through the city at 35 miles per hour, and up ahead, the red light, the stoplight is starting to turn yellow. So you know you have to slow down. So your speed is slowing down. The rate of change of your speed is changing, and that's what we call acceleration, right? If I speed up after that light turns green again, I'm going faster. I'm speeding up. I'm accelerating. As I approach the red light, I'm decelerating. So the second derivative is my change in speed, or the change in the rate of change of the rate of change of position. Does that make sense? So the rate of change of the rate of change of position is acceleration. The rate of change of position is speed. Now, that is a mouthful, and these can be challenging to interpret, and I usually do have interpretation problems on tests because I think it's really important, not that you know how to do just the formulas and the calculations, but you understand what the hell you're doing. It will serve you so much better in your career and in life if you understand the concepts behind this math, not just the calculations behind the math. All right, so now let's look at one more example, example 7. Notice this is the same problem that we did the first and second derivative for, x cubed minus x. So notice in example 6, we found that the second derivative of this was 6x. We found the first derivative way back in example 2. So now we need to take the third derivative here, f prime 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 of x, and notice here's f of 4, the fourth derivative of x. All right. Now notice that the second derivative of x is 6x. This is a straight line with a slope of 6. And remember that the third derivative is equal to the slope of the second derivative. Okay? So since the second derivative is a straight line with a constant slope of 6, that means the third derivative is just going to be 6. We don't even have to use the formula because we are so smart and we remember our algebra, and we know that a derivative is equal to the slope of the function. The second derivative is the slope of the first derivative. The third derivative is the slope of the second derivative. And since the slope of the second derivative is a constant 6, we have that the third derivative equals 6. Now the fourth derivative is the slope of the third derivative. Now think about this. What does this function, or what does this graph look like if the third derivative equals 6? Well, remember, this is saying y equals 6, right? If we think of the third derivative as a function, which it is, which is a horizontal line, a straight across line at y equals 6. What is the slope of a horizontal line? It's 0. So once we got to the constant here, our next derivative is 0, and every other subsequent derivative is also going to be 0. So once we get down a few levels into the derivatives, each one should get a little bit easier to calculate, and we should eventually end up with 0.